Here I'm going to talk about the Frayer diagram for the mathematical model of 1D, 2D, 3D sinusoidal waves and wave speed. So its definition is that the mathematical model could predict the displacement of the particle given its position, time, and phase constant. And what it means is when we look at the equation here, when it is 1D and one particle at different time, this is the equation here. And the displacement is given in terms of meters, amplitude given in terms of meters, and then the wave number given in rad meters inverse. And then this is the angular speed. The angular speed is in radians seconds inverse. And then the finally phase constant is given in terms of radians. So this is the wave function of a certain wave, and in the wave number, k is equals to 2 pi over lambda, where lambda is the wavelength, and w is the angular. It should be angular speed here. It should be angular speed, and it would equals to 2 pi f, which is the angular frequency, and it is equals to 2 pi over t, which is the period. So the phi naught would be the phase constant. And when we're saying that the wave is traveling to the left or counterclockwise in Frayer diagram, so in here Frayer diagram is traveling clockwise. So this would not be the case. But if it is traveling counterclockwise and the wave is traveling to the left, then here this is positive. But if it is traveling to the right or clockwise, then this would be negative. And the wave speed is given by v equals to f lambda. I don't know why I included 2 here. I should delete 1. I'll delete this one. So if we're talking about the wave speed, then we're saying that v is equals to f lambda, or if we're converting in terms of the angular speed, and wave number would be angular speed divided over the wave number. And in 2D and 3D, it is essentially the same, except this time the amplitude is given in terms of the position of the particle, because this is the limitation and applicability, is that for 1D, the phase is constant. For 1D, 2D, and 3D waves, the waves is sinusoidal, but when it is in 2D and 3D, the amplitude decreases as the waves moves forward, or as the position of the particle is further. That's why A is written in terms of R, because as R gets larger and larger, then A should be smaller and smaller. And this is some related helpful diagrams. This actually helped me a lot in understanding how waves work. For this one, waves is traveling to the right, so it is clockwise as mentioned. And because at t is equal to 0, this is a over 2. So we're finding a over 2 here, right, which is here. So we have 2 points here, possible position of the particle, and we're trying to determine which one is the particle, and this one is actually given by, I'll say it's like 20 to 25 degrees. This one would be 150, 160 degrees. So we're trying to say if the phase constant is gonna be smaller than it's between 0 to 90 degrees, or it's gonna be between 90 to 180 degrees. And for this one, the left side, it is gonna be between 0 to 90 degrees for a reason. It's because when we're looking at this this diagram here, as the wave is traveling to the right, this particle essentially moves downwards. So the only possible case that the particle would move downwards is when it's between 0 to 90 degrees. And the same thing here, when this is traveling to the right, this particle would actually move upwards. So it's gonna move here. As the wave travel to the right, it's gonna follow that line and moves upwards. And that's why this time the particle is here and not here. And it would be between 90 degrees to 180 degrees. This is 0, this is 90, 180, and this is 220, yeah. So that basically concludes the Frayer's diagram for the mathematical model of 1D, 2D, 3D sinusoidal waves and wave speed. Thank you.